Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, are the robots evolving? And how does that thing work? Hello everyone, welcome to Robot Talk. I'm your host, Claire Asher, and this week we're coming back to one of my favourite topics, robot evolution, with a guest whose self-assembling robots could one day explore other planets. Before we get started, I'd like to remind you to rate this episode and leave a review if that's something you can do on the platform you're listening on. And don't forget to share the podcast on social media or tell your friends about it. It really helps the podcast reach more listeners. And a quick shout out to my new Patreon supporter, Myra. I can't thank you enough for supporting the podcast. Welcome to the Robot Talk community. So, with all that said, I'm excited to introduce this week's guest. I recently had a fascinating chat with Emma Hart from Edinburgh Napier University about algorithms that evolve better robot designs and control systems. Today, I'm chatting to Emma Hart, a professor at Edinburgh Napier University who's developing algorithms that evolve new robot designs and control systems. Hi Emma, wonderful to have you on Robot Talk.
Hi Claire, it's a pleasure to meet you.
So, the robots that have been sent to explore other planets so far have all been, really carefully and precisely designed by roboticists on Earth. But you're working on an alternative approach that would instead transport the equipment needed to build robots on the planet, and which can then be evolved to adapt to whatever environment they find there. So can you kind of talk us through how this process could work?
So you're absolutely right that to date, when somebody wants to send a robot to another planet, it's very, very carefully designed here on Earth. Then you have to put it in a rocket or spaceship. It might take 10 years to reach that planet. And then you might find when you start to try and do experiments that maybe, there's not enough friction on the wheels. It doesn't have the right kind of implements to take a sample or clamber over rocks. And of course, that's very expensive in terms of time and cost in getting it there. So even if we can do our best, as an engineer on Earth to try and envisage what we might find on these faraway planets, we're probably never going to get it exactly right.
Yeah.
So we kind of wanted to change the approach to say, well, rather than kind of pre-designing for what we think we might find, what if instead you could send a kind of technology, a kind of factory in a box, let's say, that you could send the factory to the planet. When you get to wherever it is that you need to explore, you could use technology, cameras and things to basically understand what the environment looked like. And then you could use a machine, some sort of generative artificial intelligence, to design a robot that was exactly specified to the environment that you found. So you would need some kind of AI to actually do that design.
Yeah. But
then you also need some sort of engineering technology, because having done the design and perhaps simulated it inside a computer to make sure it worked, then you have to have something that can automatically build the robot. So in some of the work we did, there was a lot of effort went into this engineering process of being able to actually fabricate a robot, for example, 3D printing parts and doing all the wiring. And then as long as that process has gone well, you could then put the robot out into the environment. But probably it would still need to adapt, because the first versions of it might not quite be right.
Yeah.
So what we kind of envisaged, you could even imagine a colony of these robots gradually adapting over time. It's a little bit like biological evolution, of adapted species to a very specific niche.
Yeah.
And it's the same kind of thing, that you would hope that your robots would gradually adapt to the environment they find themselves in. So if they needed kind of a bit bigger wheels or a bit longer drills, then this could also happen by, going back to the factory to have parts added on or parts removed until you get the robot that exactly is right for the thing that you need to do. So that this is the overall vision.
Yeah. So it's kind of taking some of the principles of evolution and then tweaking it a little bit to work for the situation that you're kind of designing the system for.
Yeah, it's exactly that. It's trying to sort of mimic the principles behind biological evolution, where you have a population of things that have some diversity. You know, some things are a bit bigger, some things are a bit smaller. And of course, in biological evolution, it takes a very long time to evolve anything, you know, thousands of millions of years. But you can do that evolutionary process. You can mimic that inside a computer very, very fast and essentially run many, many generations in, you know, hours or even minutes sometimes.
Right, yeah. So yeah, the evolution itself is kind of going on inside the computer rather than like the robots don't have to have babies.
Exactly. So although I guess in a sense, sort of at a high level, what we're doing inside the computer is essentially taking the blueprints, the DNA, if you like, of two robots and mixing their blueprints together to produce you could call it a child robot that has some characteristics of each of its parents, just like biological evolution works.
Yeah. And then I guess you'd produce multiple offspring that are each a little bit different and then see which ones actually do the best.
Absolutely. And then basically we would follow exactly like natural evolution, the kind of survival of the fittest principle. So you would produce a diverse array of robots, you would see which ones work best, and then you would selectively choose the good ones to produce the next generation. And by basically biasing the selection towards good robots, you kind of evolve towards better and better robots over time.
Yeah. I guess the other advantage to this is if the environment changed for some reason, or I guess on Earth there are lots of different environments, maybe there'd be different areas of this planet that would be different. You can kind of keep adapting to these new conditions.
Yeah, I think that's really important, because I think a lot of the robots that we make at the moment to work in factories and things, and use cases here on Earth, they have a very specific kind of remit, and they don't work well in a new situation. And that new situation could be because the environment's changed. You know, you've come across some kind of different type of terrain you didn't expect. But it could also be because something like broke on the robot, for example, like one of its legs got slightly bent or something. And so then it has to kind of adapt its own behavior to cope with that. And we see this in animals a lot. They're able to adapt. You sometimes see dogs with 3 legs who are able to walk perfectly well. So this adaptation is really important to make the robot have a long life, a useful life, in order to adapt to new situations, but also to adapt to changes to its own body.
Yeah. Probably when people think about evolution, they think about like your physical characteristics changing, but of course it also applies to behavior.
Absolutely.
And I guess you're evolving the robot body and the robot brain.
Yes, that's a really important part of it. So we're evolving both simultaneously, but sometimes you might kind of want to, once you have a body that works well, you might want the brain to then carry on adapting. It's a little bit about like, a human learning over its lifetime. I don't know, if you learn to play the piano or something, you get better and better at doing something the more you practice it.
Yeah.
So your body doesn't change, but the way you use your body changes. So we can do that exactly the same in the robot. We can keep its body fixed, but then keep a kind of learning process running in the robot's brain, so it finds different ways to adapt to different situations.
And so, as you mentioned, like one key aspect to the way biological evolution works is that your brain and your body are kind of pre-programmed by genes that are encoded in DNA. So your evolving robots, do they have a set of genes that kind of contain the instructions for how they look and how they behave?
Exactly that. So typically we have a kind of what we could call it a genome or a chromosome. It's normally in 2 parts because it's easier to code like this just for computational purposes. So half of it kind of encodes the body. What does it look like? What sensors has it got? What kind of actuators does it have? What its shape is, what its size is. And then you have another half of the genome that encodes the brain, that is basically, for example, taking in input from the sensors and translating that into actuation and behavior and movement of the robot. And so each robot kind of comes with its own blueprint, its own piece of DNA.
Yeah.
And then this evolutionary process is basically mixing these blueprints together to try and find which is the right combination of DNA to make the robot that you want.
Yeah. I guess, to a certain extent, you're determining the ways in which the robot could change by deciding like what you're encoding in genes. if that makes sense. So like you mentioned size being one. If you have a gene for size, then it can change its size. If you didn't have a gene for that, it wouldn't be able to evolve in that direction. So you're kind of, there's a little bit of extent to which you're determining the potential when you're deciding what those genes are.
Yes, that's right. So we have to kind of specify what these genes should encode, whether it's size, whether it's, for example, like quite often in the work we do, we don't allow the evolutionary process to evolve kind of new types of sensor, but what we can give it is like an array of possible sensors that already exist that sense different things. And then the genes can code for which of these sensors should we use and where should we place the sensors.
Right, yeah.
But we're pre-specifying what's available to it. I mean, I guess a really future extension of this work, if you could like evolve your own electronics, and which actually is starting to become possible, actually.
Really?
In a very simplified way. But like in the future, it could be a way to go that you could actually evolve new types of sensor. But at the moment, we're sort of specifying a range of options, if you like, and allowing the genetic process to kind of choose the best options.
Yeah, I mean, I guess what you were talking about at the beginning about, actually having to build the robots, and so therefore you need like 3D printers and things that can wire it up, and you have to send it up with, I guess, some pre-made sensors.
Yes.
So you've kind of got robots building robots.
Yes. It all sounds a bit scary, doesn't it?
Yeah, I guess you can imagine a runaway process where you just end up with huge swarms of robots roaming this planet.
Yeah, so in a sense, you can kind of control whether it can run away or not, because if you have a finite amount of material, if you have in your factory a certain number of sensors and a certain number of wheels and a certain number of joints, then you have to recycle those parts. You can't keep making new parts. Yeah. So there's only a finite number of robots that you can actually build. So unless the robots can start, mining materials from themselves and turning that into things, in principle, the process can't run away. I think it's an important point, though, because if you have a kind of process of robots building robots, you need to have a way of essentially having an emergency stop button and stopping that process so it doesn't get out of hand. Yeah.
So, what do you see these robots doing on other planets? Exploring, maybe building new colonies for humans?
So, I mean, building is, that would be a very nice goal. I think that's quite far in the future, but I think at first, at least just exploring and sampling and being able to get to places that kind of pre-made robots might not be able to reach because they're not of the right form. But it is, I guess, in theory, it's possible that the concept at least would scale up to being able to build things.
Yeah. Okay. So what kind of stage is this research at? Like, how close are we to you actually being able to make this a reality?
So we just last year finished a project. It was a joint project between my university, Edinburgh Napier, the University of York, and the University of West of England, and a university in Amsterdam, the Free University, where we basically built a proof of concept. So it was basically half an engineering project to build the sort of factory part that could automate the manufacture, and half an AI project, I guess, to write the software that mimicked the evolution. So we managed to have an end-to-end process. So we would specify a task. We need a robot that's able to climb over to obstacles and find its way to a certain place within an environment that we could build.
Okay.
We would run this evolutionary process in simulation on the computer. It would then be sent to this kind of manufacturing process where it would 3D print like the body, like the chassis of the robot, and then it would have access to a library of parts. So we would have preformed sensors, wheels, caster wheels, like joints, like legs that can move. And then a robot arm would assemble the robot. So first of all, it would do the 3D printing, and then it would assemble the robot, and that would include so the robot had like a small computer, a Raspberry Pi in its kind of central body, and the assembly process would also automate all of the wiring up of like the sensors to the brain. And actually, probably this was the most difficult part. You could imagine a machine trying to kind of wire things together and getting everything all tangled or things working out. So a lot of work went into this engineering process. But then in the end, the arm would pick up the preformed robot and put it into an arena, and then we could watch with the camera and so kind of evaluate how it was working. So, of course, these were very simple robots. They were made out of plastic. They had wheels. They had kind of jointed legs, so they could crawl a bit like a spider.
Okay.
And they had an array of sensors. I guess it was a proof of principle that the process works end to end. Of course, like if you were really going to do this on a planet, you'd need much more robust materials, I think, than plastic to print it with. But I guess it's a proof of concept that it can work.
Yeah. How did they get on with their task?
Well, surprisingly well, actually.
Okay.
And it's also really interesting to see. So, as humans, you have very preformed ideas about, what kind of thing might emerge from this process. But of course, a computer has no ideas. It's just trying to maximize the performance on the task that you gave it. So we got quite interesting robots like appearing from some of this. So it's like some of them look surprisingly like animals, where I sense things like spiders with like lots of legs. But quite often they would have like a mixture. So they might maybe have some sort of legs that they could crawl on, but with some wheels at the back to stabilize the robot itself. We tried some in environments where like the robot had to navigate, like imagine through a maze with walls. And we even found that the process could evolve like a robot that had like a tall tower with a sensor on the top so it could see over the walls, which meant that it was very easily able to navigate around. So it's quite surprising how a process that is essentially blind, all it's told is find a robot that maximizes the performance on the task, but was able to do that.
Yeah. This is why I really like this idea, is that it can come up with something completely new that a human would never have thought of. It's interesting that it quite often ends up looking at things that real evolution created.
Absolutely. And I think real evolution is what emerges is very much influenced by the environment. And we saw that happening. So, for example, if you have a flat arena, then we tended to get robots with wheels because they're perfectly adequate to navigate that. But as soon as you put like any kind of rough terrain or, for example, slopes and things, then you would get robots emerging more that had legs because you need legs to kind of, climb over holes or climb over barriers or something like that.
Yeah, it's really cool.
So it's quite surprising. You can get quite creative things coming out that, a human engineer wouldn't necessarily have designed.
Yeah, definitely. So here on Earth, what kind of tasks or environments do you think this approach might be applied to?
So I think it's really useful for the kind of environment where it's really hard to envisage what kind of robot you would need. So a really good example of this is decommissioning a nuclear reactor, where you can't send people in to this environment, but you could perhaps send a robot factory in to design the kind of robots that you need. I guess the other sort of similar thing is undersea exploration, again, where you don't know the right kind of environment. So I think it makes sense to do it for environments that you don't understand well, even maybe glacier exploration or, difficult terrain, I don't know, rainforest or something like that. I think there's some environmental applications where you don't, you might have some knowledge of the terrain, but you don't know precisely what it is that you might find, or you at least need the robot to be able to adapt. And I think the other thing is that even in environments where you do know what they look like, I think the technology could be kind of like used in a slightly different way to, for example, design a different kind of robot. So here I'm sort of thinking of things like maybe you want a robot that's, for example, made out of more sustainable materials. Okay. But like if you're going to design, I don't know, a robot made out of bamboo or something, you need to change the design. You can't just take an existing design and build it out of bamboo because the robot will just bend or it won't have the right kind of things. So I think this is not what we really did so far, but I think you could really adapt this technology to saying, okay, we can design robots and build robots using a machine. So let's say now we want to design like robots that are made out of sustainable materials, or robots that are really lightweight, or robots that have a certain property. So even when you know kind of the application, you might be able to get a completely new design that wouldn't have come from an engineer who's taught to think in a certain way.
Yeah, and I guess once you've set this system up, you can kind of give it different parts, give it different robot DNA, and it will still kind of work the same principle.
Yes, so because the principle is basically exactly the same, so you can swap in different kinds of parts and sensors and things. Yeah.
So the one you made so far, the kind of proof of concept, how long does it take to build a robot with that?
Okay, so probably the longest part is the simulation. So the first part of the process is everything happens in simulation, because you can obviously simulate things much faster than you can test for your robots. Although you have to, because there's quite often a gap between the quality of the simulator and what happens when you actually build the robot in real life. You have to mix the two processes together and build some real robots just to check that they're behaving in reality like they do in simulation. So the simulation can take, well, it depends on the task. I guess it can take anything between hours and a few days, depending on how hard the task is. And then I guess it's more dependent on the quality of your printing process. So 3D printing can be a slow process if you want to print to a high standard. So again, that's probably going to take hours rather than days. But then actually, once you've printed the parts, the job of putting them together in an automated way is not a particularly time-consuming job.
Okay.
So it's kind of hard to put an exact number on it, but somewhere between 1 and a few days, I guess.
Okay. So what is the strangest or most surprising robot design you've developed with this kind of evolutionary approach?
Good question. So I think this one with the tower that could see over walls was like, it makes total sense, but it's quite surprising to see it happens.
It almost feels like cheating.
Yeah, of course, but why not?
No, yeah.
Yeah, I mean, we quite often get really strange things that have all kinds of mixtures of like legs and wheels that don't seem to make sense. But then actually when you see them moving, sometimes like the wheels are just helping it balance somehow. They're not really there to make it move, but they're somehow just like stabilizing the robot.
Yeah. I guess in biological evolution, sometimes you see features that like they stick around after you stop kind of needing them because they're not actually harmful. I'm thinking like, animals that live in caves but still have like kind of residual eyes left, even though they can't see and they live in total darkness. Do you see any kind of residual things like that ever turning up?
Yes, so that can totally happen because the way this evolutionary process works, you're kind of rewarding robots that do a good job, but you don't penalize them necessarily for having useless parts. So you definitely do see things where, maybe in the early stages of evolution, it was useful to have a sensor in a certain position, but as the robot changes over time, then that sensor becomes redundant, but it doesn't get removed because it's not harming it. So there's things that you can do in this evolutionary process. I mean, you could set up the evolution so you did penalize waste, I guess. Generally, we have an objective, which is like maximize performance on the task, but you could also say maximize performance, but make the most lightweight robot possible or something. And then you might start to have the evolutionary process remove some of these redundant things. But you definitely see these parts that are essentially hangovers from the early part of the evolutionary process.
It's fascinating.
Yeah. So, I mean, we come at it from a robotics point of view, but I think that the idea, and there's some groups in the world now, like some biologists who are now looking at robotics as essentially a platform to test out ideas about evolutionary biology. So, we only have one Earth and one evolutionary process to study here, and you can't obviously mimic evolution fast enough for science. But like there are several groups I know of around the world now that are now building robot platforms to totally test ideas and theories about actual evolution. So I think that's a really interesting kind of spin-off of the idea, actually.
Yeah, that's really cool. It must be so exciting to like see what the algorithm comes up with.
Yeah, and I think also it's going to really change in the future. I think what's really changing robotics now is new materials. So we tend to think of robots as, very rigid things that can't change their shape like as they're moving. But now we have all of these kind of soft and flexible materials that, if you change the current through the material, you can change the properties of the material itself. So you can make it stiffer or softer. And this enables robots to basically change their shape while they're operating. So to squeeze through a gap or find some way of, climbing over the objects. So I think I think this is what's going to drive like really innovative robotics in the future, combined with these kind of AI processes that can really capitalize on that. And I think then we will start to see robots that we don't recognize as robots now anyway, that humans would design.
Yeah, definitely. Yeah, that sounds really exciting. I would love to see an evolved soft robot.
Yes. I mean, people are doing it. I mean, people have built them, but they tend to be quite sort of modular. So if you imagine like cubes of soft material, so you get very kind of regular looking robots. But I think this is changing very fast now.
Yeah. Emma, it's been fascinating speaking to you today. I've been talking to Emma Hart from Edinburgh Napier University. Thank you.
Thank you very much for your time.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. It really helps boost the podcast, so thanks in advance. And make sure you check out @RobotTalkPod on social media to see a photo of an evolved robot that can navigate around obstacles, which Emma developed. Next week, I'll be speaking to Laurel Pinto from New York University about adaptable robots for the home. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.